The closer you get to the edge, the slower time goes. The light around you bends into a halo. Your heartbeat stretches. Molecules rip apart. And then, you cross the line of no return. This is what happens to you if you fall into a black hole. This is the event horizon, the most mysterious boundary in the universe. The event horizon is not a physical wall. It is a point in space where gravity becomes so strong that not even light can escape. Once you pass it, the universe as you know it ceases to exist for you. There is no going back. No signal, no cry for help, no last message can ever reach the outside world again. If you watched someone fall into a black hole, you would see them freeze at the edge, their image fading into nothingness. But for them, time runs normally. They cross the threshold, unaware that to the outside universe, they have already vanished. As you fall deeper, gravity's grip becomes unbearable. The difference in force between your head and feet is so extreme that your body stretches like molten glass. Molecules tear apart. You become a stream of atoms spiraling toward the center, a process scientists call spaghettification. For a stellar mass black hole, this happens in seconds. For a supermassive one, you might survive minutes, long enough to realize what's coming.
Time and space must disappear altogether at the singularity. This is the most remarkable feature of Einstein's equations.
At the very center lies the singularity, a point where density becomes infinite, where space and time break down. The laws of physics as we know them no longer apply. Here, time itself may stop, or loop, or lead to another universe entirely. We simply don't know. What if black holes are tunnels to other realities? What if, instead of dying, you emerge somewhere, or somewhen else? For decades, scientists believed nothing escaped black holes. Then Stephen Hawking proved them wrong. Black holes can die. They slowly evaporate, leaking radiation over trillions of years. But here's the catch. The radiation is random. No information escapes. It's as if the universe itself forgets what fell in. If information is truly lost, it violates quantum physics. If it's preserved, where does it go? This debate still rages today. Black holes are not just cosmic destroyers. They are laboratories for the most extreme physics imaginable. They bend time. They warp space. They might even be gateways to places beyond our universe. The greatest discoveries in black hole physics are still ahead of us. And one day, we may finally answer the question, what truly lies beyond the event horizon? Imagine throwing a book into a fire. The pages burn, the words vanish. But in theory, if you could track every atom, every photon of heat, you could reconstruct it. Now imagine throwing that book into a black hole. According to Einstein, it's gone forever. According to quantum physics, that's impossible. This is the greatest contradiction in modern science. The black hole information paradox. In 1976, Stephen Hawking dropped a bombshell. Black holes don't just trap matter, they erase information. This violated a fundamental law of quantum mechanics. Information must always be preserved. If Hawking was right, reality itself has a delete button. Why it matters. If information can vanish, the past is unknowable. The entire framework of quantum physics could be wrong. Physicists were forced to choose. Einstein or quantum theory. The scientific community split. War was declared. And the battlefield? The event horizon. In 1997, Hawking made a famous bet against physicist John Preskill. He insisted information was destroyed. The stakes? An encyclopedia. Not just any encyclopedia, the complete baseball encyclopedia. Because even geniuses have a sense of humor. The shocking twist. In 2004, Hawking conceded. He admitted black holes might preserve information after all. But how? The answer would rewrite our understanding of space-time. What if everything that falls into a black hole isn't lost, but encoded on its surface? Everything you see, touch, and experience, your memories, your emotions, even this video right now, is just a 2D projection from the edge of the universe? This isn't philosophy. This is the holographic principle, and black holes might be proving it true. In the 1990s, physicists stumbled on something bizarre. The math said black holes store information on their surface, not inside. Like a DVD where the movie isn't in the disc, it's encoded on the label. Like your smartphone screen, millions of pixels create a 3D illusion, but the image is really flat. Now scale that up to cosmic size. The universe's screen is the edge of space itself, and we're the pixels. Evidence. We're hunting. Black hole entropy matches 2D surface calculations perfectly. Quantum gravity models suggest space is pixelated at tiny scales. Cosmic microwave background might show holographic static. Maybe black holes aren't destroying information, they're just saving it to the universe's hard drive. Mind-blowing implications. The event horizon could be a hologram, projecting reality inward. The universe itself might work this way, a 3D illusion painted on a 2D boundary. If true, we could all be living inside a black hole's holographic projection. Is our reality just a shadow of something deeper? Some physicists now believe crossing the event horizon isn't peaceful. You might hit a firewall, a wall of energy that vaporizes you before reaching the singularity. Others argue black holes are fuzzy balls of strings, not smooth tunnels. The debate is far from over. What this means for us. Black holes could be cosmic glitches, revealing flaws in our theories. They might be the key to unifying gravity and quantum mechanics. Or they could be something we haven't even imagined yet. Here's the ultimate plot twist. Our universe might be inside a black hole in another reality. Here's why some physicists take this seriously. Clues that fit. 1. The Big Bang's singularity looks suspiciously like a black hole birth. 2. Universal expansion mirrors how black holes stretch matter. 3. Cosmic background radiation patterns match holographic predictions. Why it's hard to prove. We can't see outside our universe, if there even is an outside. The parent black hole's physics might be completely different. Turns out, The Matrix was a documentary. Where's my red pill? How do you test if reality is a hologram? Scientists are getting creative. Current missions. Fermilab's holometer measures quantum fuzziness in space-time. Black hole simulations using ultra-cold atoms. Gravitational wave detectors hunting for holographic echoes. What success looks like. Finding pixel-like patterns in empty space. Detecting information leakage from black holes. After decades of research, we still don't know if information escapes black holes. But one thing is certain. The answer will change everything. It could reveal hidden dimensions. It could prove we live in a hologram. Or it could show us that reality is far stranger than fiction.
The universe is under no obligation to make sense to us.
Imagine folding a piece of paper so two dots touch, then poking a pencil through. That's a wormhole, a tunnel through space-time itself. Einstein's equations say they could exist. But are they real? And if so, where do they lead? In 1935, Einstein and his colleague Nathan Rosen found something bizarre in the math of general relativity. They weren't looking for wormholes. They were trying to describe particles. But the equations revealed bridges connecting distant points in space. They called them Einstein-Rosen bridges. The scientific world shrugged. Until now. How it works. 1. Think of space-time as a stretched bedsheet. 2. A black hole creates a deep funnel in the sheet. 3. If another funnel connects to it, you get a tunnel, a wormhole. Problem. The equation said these bridges would snap shut instantly, like trying to walk through a slamming door. To keep a wormhole open, you'd need something with negative energy, a material that repels gravity instead of attracting it. Weirdly, quantum physics allows this, in microscopic amounts. Exotic ingredients needed. Negative energy. When two metal plates are placed extremely close in a vacuum, quantum fluctuations create negative pressure between them. It's real. We've measured it. But for a wormhole, you'd need amounts we can't produce. Theoretical matter. Imagine a substance that pushes space outward instead of pulling it in. Physicists call it exotic matter. Does it exist? Maybe. In theory. Why it's so hard? Even if we found enough exotic matter, calculations suggest a human-sized wormhole would require more energy than exists in our galaxy.
If time travel is possible, where are the tourists from the future? Stephen Hawking.
Wormholes don't just connect space, they could link different times. Move one end near a black hole, where time slows, and you've got a time machine. But here's where it gets messy. Grandfather paradox. You go back in time, accidentally prevent your grandfather from meeting your grandmother. Result? You're never born. But if you're never born, how did you go back in time? Physics solutions? 1. Self-consistency. Novikov principle. The universe corrects itself. Your actions in the past already happened. You can't change them. Example. You try to shoot your grandfather, but the gun jams. Always.
You just got jammed.
2. Parallel timelines. Multiverse. You don't alter your past. You split off into a new timeline. Example. Kill your grandpa? Congrats. You just created a parallel universe where you don't exist. Are wormholes already out there? Some physicists speculate tiny wormholes flicker in and out of existence everywhere due to quantum foam, a seething ocean of microscopic space-time bubbles. Others think supermassive black holes might hide them. Why we haven't found them? Too small? Quantum scale? Too unstable? Collapse instantly? Or we're looking in the wrong way? What if dark matter is actually wormholes? Wormholes tease us with possibilities, faster than light travel, journeys to other stars, even time machines. But for now, they remain just out of reach. Maybe one day we'll unlock their secrets. Or maybe they'll remain the universe's best-kept shortcut.
In theory, theory and practice are the same. In practice, they are not. Albert Einstein.
Black holes suck. Literally. But what if the universe has emergency exits? Cosmic fire escapes where matter gets spit back out. Meet white holes. Black holes, rebellious twins. They're mathematically possible. But do they exist? And more importantly, could one suddenly open under your bed? If a black hole is a cosmic drain, water swirls down, vanishing forever. A white hole? That's the same drain in reverse, blasting water upward violently. Nothing can enter, only exit. Key features. No entry allowed. Unlike black holes, you can't fall in. You'd be repelled. Infinite energy. They'd explode matter like a cosmic sneeze. Time-reversed black holes. Einstein's math works backward, too. White holes are shockingly rude. They violate the second law of thermodynamics, the universe's no-cutting-in-line rule. Here's why they're probably extinct. Instant death by physics. A white hole would explode instantly, like a soda can shaken for 13 billion years. Any matter inside would vaporize in a burst of energy. Black hole, normal time. Matter falls in, gravity crushes it, singularity grows. Lasts billions of years because it feeds on new material. White hole, time reversed. Matter must explode outward, like hitting rewind on a black hole. No new matter can enter. It's a one-way exit. So all its energy erupts at once, like uncorking a champagne bottle. Some physicists think the Big Bang was a white hole, a singularity vomiting space-time into existence. Wild? Yes. Possible? Maybe. Evidence? Well, clues we're hunting. Gamma-ray bursts. Some odd explosions could be dying white holes. Dark energy sources. Unexplained cosmic fireworks. Quantum gravity models. New math says white holes might flicker briefly. Or maybe white holes are just black holes from an alternate universe, vomiting their lunch into ours. Physics is weird. Hypothetically, if you could reverse a black hole's time, voila, white hole. But here's why that's a terrible idea. Energy apocalypse. Requires negative energy, which we can't make in bulk. Would detonate with the force of 1 million supernovas. Time paradoxes. Might accidentally rewind yourself out of existence? Insurance definitely doesn't cover this. White holes remind us that the universe is stranger than fiction. They might be extinct, they might be hiding, or they might be the key to understanding the Big Bang itself. One thing's certain, if we ever find one, physics textbooks will need serious updates. What if I told you there are places in space where time slows down so much that while you blink, years pass on Earth? Where a 5-minute chat could mean missing your own funeral? Welcome to the warped world of black hole time travel. Picture a river flowing toward a waterfall. The closer you get to the edge, the stronger the current pulls you. Now imagine time as fish swimming in that river. Near the waterfall, black hole. The current drags them so fiercely they barely move forward. But farther upstream, time fish swim normally. That's gravitational time dilation. The waterfall's pull slows time itself. Key facts. Near a black hole, 1 hour for you equals years on Earth. This isn't sci-fi. It's verified by atomic clocks on GPS satellites, which have to adjust for Earth's weaker gravity. The effect gets extreme near the event horizon.
The truth is sufficiently complicated to be interesting, but not so complicated as to be incomprehensible.
Remember Interstellar's water planet where 1 hour equals 7 years? That's real physics. But here's what the movie glossed over. What's accurate? Time dilation gets worse the closer to the black hole. The frozen astronaut effect, Miller's planet. What's stylized? Gargantua spins too fast. Real black holes max out at approximately 94% light speed. The tidal forces would have shredded the planet. In reality, Matthew McConaughey would have been turned into astronaut spaghetti long before the emotional ending. Here's how you could time travel to the future right now. Orbit near a black hole's event horizon for a few hours. Return to Earth thousands of years later. Why it's pointless? It's a one-way trip, no going back. Everyone you know will be dead. You'll need a ship that survives spaghettification. Great for avoiding student loans, terrible for family reunions. Black holes prove time isn't universal. It's personal. Your watch ticks differently based on where you stand in gravity's grip. Maybe time travel isn't about machines, but about finding the universe's natural shortcuts. If this cosmic revelation blew your mind like a supernova, do the universe a favor. Hit that thumbs up so YouTube's algorithm sends this to fellow reality questioners. And subscribe if you want more mind-bending science that makes black holes look simple. Who knows? Maybe in a holographic universe, every click creates another you in a parallel dimension. And that version definitely subscribed already.